Okay, so just for those of you that are new and haven't, if you wasn't at the session on Monday. So what we're going to do is going to work through module 1 today. So we're going to look at atomic structure and the periodic table. It is for separates and combined. I will let you know when it is just for separates. That is right at the end. There's just a small section on transition metals. It would still be useful for you to listen to and look at this type of exam questions. But if you do want to leave when we go into separates, that is absolutely fine. Just a quick overview then of your exams then. So separate science, obviously you sit 3 exams. Combined science, you are going to sit 2. And so they're assessed slightly differently. So your separates are 100 marks per paper, whereas your combined are 70 marks. So the length of the paper is a little bit longer because you cover that little bit more content. Okay, now in today's session, there is no required practicals and there's only a small section of separates. Okay, so there's no extra video links, etc. in this one for you today because we start with our required practicals in module 2. So things that we're going to run over today then, we're going to look at atomic structure, how the model of the atom has changed, so what discoveries we made, why we changed our minds on this. And then we're going to look at the periodic table and again, how the ideas of how to lay out the periodic table have changed. Okay, so what I'll do is I'll talk about key bits on screen looking at the spec. So this is from the specifications. This is directly from here, and I've put little prompts for me as well as for you as we go along, because we're not recapping as much content, we're more looking at the questions. Obviously we'll recap content and chat about it as we go through. So we're going to recap definitions of atoms, elements and compounds. We're going to look at mixtures. Oh, sorry if I click on the right screen. Eventually. Why does it want to move? Come on, let's play. And we're going to look at the development of the atomic model. So what do we start with? So hopefully this little sort of infographic is bringing it back. So we started with it being an indivisible object, so a solid sphere. And then obviously now we know that we have a nucleus of protons and neutrons and the electrons orbit around the outside. So it's about how did we get from thinking it was a solid sphere to where we are now. Okay, let's jump in. I don't know why this won't let me change slides. Okay, so we're going to start with some of the more straightforward questions. Sorry, I was just checking them when it says substance B contains 2 types of atoms. I thought I'd chopped off a picture, but I haven't. Okay, so elements, compounds, and mixtures then. So, an element being 1 type of atom. Let's put space in it so you can see what I've written. A compound is 2 or more atoms, and a key thing here is that they are chemically combined. And then we have a mixture. Bring this down here. So 2 or more could be atoms, molecules. We could use the overarching term of particles. So 2 or more atoms and molecules that can be separated. Okay, so In this question then, it says substance A contains only one type of atom. Hopefully you should have that now that I've just given you those definitions. So substance A does not conduct electricity. Which type of substance is A? Tick one box. And then the same here, but we've got a slightly different definition. Contains two types of atoms and they are chemically combined. Which type of substance is B? Okay, just going to let someone in and then we'll mark it. Okay, so make sure that you only tick one box. Okay, so substance A is one type of atom and it says it does not conduct electricity. Well, if it's one type of atom, it's going to be an element. So it's brought it down to these two, and it does not conduct electricity. Okay, metals do conduct. Apologies if you can hear my doggies. And the non-metal does not conduct. If you make a mistake, so if you tick a box and you decide that you don't want that one, make it really clear that then that is not what you are doing. Because if you do tick it, forget to cross it out, and you then tick the right box, you've ticked two boxes, so you wouldn't gain the mark. You can only tick one because essentially what you could do is just go through and tick them all. Well, one of them is going to be right. Yeah, so make sure that you only tick one box. Substance B then, two types of atoms chemically combined is a compound. Okay, those of you that I've just let into the group, just a reminder that chat function is open. You may ask questions in there, or we'll do them at the end. It's entirely up to you. Okay, so this is sort of obviously a diagram view of it. So they've given you diagrams to decide on what they are. This question is about elements, compounds, and mixtures. We've got 5 different substances, and it tells us that the white circles and the black circles represent atoms of different elements. Okay, so that's given us a bit of extra information here. Use figure 5 to answer these 3 questions, 1 mark each. And again, we've got that just tick one box. Make an error, make sure it's obvious that you've crossed that out and which one you are ticking. So which substance is only one compound? Okay, so remember a compound is 2 or more elements joined together, which brings me down to B, C. But it's just one compound. We've got 2 different types in here. We've got 1 black, 1 white, and here we've got 2 white and 1 black. So one compound is B. Substance which is a mixture of elements. Okay, the mixture of elements is D, because we've got, even though they are bonded together, they are still one type of atom. It's still one type, therefore it is classed as an element. Even though 2 are bonded together, it's a molecule. A compound is 2 or more different elements. Because they're the same, we still class it as an element. Which substance is a mixture of an element and a compound? Okay, so this is purely an element, compound, mixture of compounds, mixture of elements. So here we've got a compound and an element because they're the same type. Right, so we are going for E. Okay. Right, so a little bit then about models of the atom. So how that has changed. So we used to think that it was a solid sphere, something like a marble or a ball bearing. And then as we've sort of progressed, we've learned about the subatomic particles. And so we went on to think about what we call a plum pudding model, and we'll talk about those a bit more in a minute. Okay. So first question, it says that atoms were first thought to be tiny spheres that could not be divided. Which particle was discovered to change this model? And again, it's just a tick one box. Okay, so we went from being a sphere to what we call the plum pudding model. So we thought that it was like a positive dough with electrons just dotted around in it. Okay, so we discovered that they were electrons. Okay, so electrons made us realize that then we moved on to the plum pudding model. Okay, so a ball of positive charge with the negative electrodes just dotted around in it. Which leads us on to 2.2. Figure 2 shows another model of the atom. What is the name of this model? It is the plum pudding. (2.3) So a scientist. A scientist fired particles at gold atoms. Some were scattered. This led to a different result. So which type of particle was fired at the gold atom? Okay, so this is how we went from being the plum pudding model to realizing that there was space between them. Okay, so this was the alpha, these were alpha particles. Okay, so it will be this box. And the final part on this, which scientist first suggested that electrons orbit the nucleus at specific distances? Okay, so once we discovered that electrons were around, the first sort of idea is like, well, you know, what you'd see on TV, etc., that were like this. And then we realized that actually we've got our nucleus and our electrons surrounding it, as we know, in our shells. And it was Bohr that did the work that led to this. Okay, so we started out as a solid sphere, discovered electrons, so thought it was a positive dough with electrons dotted within it. Alpha particle, the alpha scattering made us realize that there must be empty space because some of the alpha particles went straight through, some of them bounced back. So we must have had some empty space for them to go straight through. And then further work was done. So Niels Bohr suggested this nuclear model, that the electrons orbit at specific distance. So that's where we then came to having shell number 1, 2, 3, etc. Okay. So this is a higher level question. Okay, so as you can see, we're now into 4 marks. Is the model of the atom changed as new evidence was discovered? Excuse me. The plum pudding model suggested it was a ball of positive charge with electrons embedded in it. Evidence from the alpha particle scattering experiment led to the change in the model from the plum pudding. So explain how. Okay, so 4 marks available. We need to say what was going on. So just to give you a reminder, so they took a gold sheet of particles, a sheet of gold particles, and they fired alpha particles at it. So alpha particles is the same as a helium nucleus. So if you think about a helium nucleus, it has got 1 positive proton and a neutral neutron. Basically, they fired them at it and they got a couple of different results. Some of them went straight through. Okay, so if they went straight through, there must be some empty space. Some of them sort of kind of deflected. So some of them sort of went off at a different angle. And then there were very few, but some bounced back. So if we bounce back, we must have known that there was something solid there for it to come straight back. And some deflection, there must be some other charge. Okay, so let's have a look at this. So we're leading from it then. So most of the alpha particles passed straight through. So this is how we came to think about the empty space. Because we know that we've got our nucleus, so our protons and neutrons are centered in there, and then our electrons are within those shells. So the ones that pass straight through must have gone through some empty space. So that told us, so the empty space, talking about the empty space and then passing through, is 1. So the mass of the atom is in the nucleus, although it's mostly empty space. So that's your first 2 marks. And then talking about that some of them were deflected or reflected. So if an alpha particle happened to hit the nucleus, where there were other positive charges, well, they're going to repel and bounce back. Yeah, if it got close to the nucleus, again, it would repel. So we get some deflection. So either that they were deflected or reflected, which shows that the atom must have a positively charged nucleus. Okay. So we're still on the sort of terms of the protons and the electrons, like the plum pudding model, but because some of them went through, we knew that there must have been empty space in there. So therefore, we moved on to this model. Okay, let's keep moving because we've lots to get through. Right, knowing the charge and the mass of protons, neutrons, and electrons, just learn it, just be able to regurgitate it, write out the table, because there are lots of questions that simply have a table of the names of the particles, the mass and the charge, a couple of blanks in the table, and you fill them in for 1 mark each. Okay. So then thinking about, just a reminder that our atomic mass number is the top number. That's my pen not want to work. We're back. Yeah. So the top number is the mass number. Remember, you get your periodic table in your exam, and this is labelled on there for you. So mass number are the 2 that have mass, which are protons and neutrons. And our bottom number is the atomic, and it is in brackets, proton number. And our protons are equal to our electrons. Okay. So let's start with some more straightforward questions. So know what the structure of an atom looks like, and know what information is on that periodic table. So we've got figure 1 represents an atom of element Z, doesn't matter what it is. It's asking us to identify, so name the parts labelled A and B, choose the answer from the box. Don't make something up, use what is there. So A is the central parts, this is the nucleus, and B is pointing to what we represent as little crosses, and these are electrons. Okay. Which particle has the lowest mass? This is where I said it's really key that you learn that table, because it is our electron. Okay. We say that our electron has 0 mass. You may have seen it as represented as 1840. Yeah, if you do that calculation, that number is so small that we don't worry about it. We don't put it into our calculations. Okay. Which group of the periodic table, so this has brought in an extra little bit of knowledge, which group of the periodic table contains element Z? Remember that the number of electrons in the outside shell tell us what group. So we've got 3, therefore we're in group 3. Give the atomic number. So the atomic number is the bottom number. If we just pop back to that. Where is it? There, put it. So the atomic number is the bottom number and the mass number is the top number. Okay. Oops, come on too far. So atomic number, the atomic or the proton number. So that equals the number of electrons because the protons and the electrons are equal. Okay, so for this, we count up how many electrons it's got. 2 in the first shell, and then 3 from our outside, which gives us 5. And that number is there, which is a good indicator. So we've got atomic number of 5. Now the mass number is the number of protons added to the number of neutrons. So for that, we're looking inside the nucleus. Okay. So we just need to simply count up how many we've got. Now we know we've got 5 protons, therefore we're going to have 5 electrons, therefore we know we're going to have 5 protons. And if we add them up, we've got 5, 6, 7, 8, 9, 10, 11. Okay, so it would just be a matter of counting them. But that's knowing what those numbers on the periodic table relate to and what information they're telling you. Okay. So then we've got, as I said to you before, just learn this table because they're easy marks. Here we've got a table. It's not got all 3 of them in. We've got 2 marks available. You will get a mark for each correct row. Okay, so our neutron has a mass of 1 and a charge of 0. So that will give you 1 mark. And then we've got positive 1. Our protons are positive, and they also have a mass of 1. So proton and 1 would give you your second mark. Okay, so a little bit about the periodic table then. So we moved from Mendeleev's periodic table. So Mendeleev left gaps. He put more than one element in a box because what he was trying to do was to link up similar chemical properties. Okay. So lots of people were a little bit wary of that. Well, you can't leave gaps, and how do you know that there's going to be an element discovered here and whatnot? So we have got some similarities. You can see that compared to our modern periodic table now, we've got groups. We're missing that midsection, so we're missing the transition elements. So they were placed in, but not quite known where to put them yet. And some of these gaps have obviously now been filled. So Mendeleev was onto the right thing. So if we jump straight into some questions, so this is both on foundation and higher. Okay, so this is in the 19th century, scientists had to classify elements by arranging them in order of their atomic weights. Figure 11 shows the periodic table Mendeleev produced in 1869. So this is Mendeleev's table. So we've got 2 elements in the same box, gaps, etc. So the atomic weight of tellurium is 128 and iodine is 127. Why did he reverse these elements? Okay, so iodine is here, tellurium is here, and they should be, if we were going purely on their weight, they should be the other way. Okay, so let's have a look. Whoops, sorry, moving the wrong screen. Okay, so if they were the other way around, so here's iodine and tellurium. If they were the other way around, then we'd have tellurium in here in a group of halogens. Okay, so iodine that has similar chemical properties to fluorine, chlorine, bromine would be in a different group. Okay, so we reverse them so that elements, so that iodine was in a group of similar properties. Okay, you could also say that if it was the other way around, so if iodine had been in group 6, then it would have different properties to group 6. It's just worth the 1 mark, so it doesn't matter which way, which bullet point, which way round you have said this. Okay. So Mendeleev left spaces, he left gaps with an asterisk. He left spaces because he thought missing elements along there. Why did, sorry, I'll start that again. Why did Mendeleev's periodic table become more widely accepted than previous versions? So initially, when he was leaving those gaps, people were a little bit skeptical about it. However, he predicted what elements, what the properties he thought they were gonna have. So because he'd done this grouping, he could predict what he thought might be found there. And eventually, those elements were discovered. And they matched his predictions. Okay. So it became more widely accepted because what he'd said and what he predicted did come out, become true, and so people started to believe it. So your 3 marks, talking about that it had missing elements. The elements where he'd left, or elements where he'd left a gap for, were then discovered, and they matched his predictions. Okay, so then he was obviously became more widely accepted because these came to be true. So Mendeleev arranged the elements in order of their atomic weight. What is the modern name for their atomic weight? So when we look at the periodic table, the top number, the mass number, it goes generally from low to high, but it's not perfect. However, if you look at the bottom number that we call the atomic number, they strictly go in order. Hydrogen 1, helium 2, lithium 3, etc., etc. Okay, so they're now ordered in what we call the atomic number. Okay, very quickly then about metals and non-metals. Okay, so and then relating and thinking about group 1, 7, and 0. So let me have a look what I've put on. Yep, so we're going to have a look at these groups, knowing what their properties are like, explaining why they have their properties. So group 1 are really reactive. Why are they reactive? How does that reactivity change down the group is what we'll look at. And then we'll do the same for group 7. Okay. So most straightforward questions to begin with. The name of elements in group 0 are the noble gases. So these have a full outer shell. So they are unreactive and they exist at what we call monatomic. They exist as single atoms because they don't need to bond with anything else. because they've got a full outer shell, they're stable. Which statement about the elements in group 0 is correct? Okay. Elements are very reactive. Well, no, they're not, because they've got that full outer shell, so they're not very reactive. They form negative ions. They're not going to form any type of ions because they don't need to gain or lose electrons. Their boiling point increases down the group. And let's have a look at the last one. So the relative atomic mass decreases down the group. So that's saying that they get lighter. The mass gets less as we go down. We've got more protons, more neutrons, and therefore it's going to increase. Therefore, we want this one. Neon is in group 0. What type of particles are in a sample of neon? Well, they are atoms. Okay, they're not ions because they don't need to lose or gain electrons. And they are not molecules, again, because they're not bonded to one another. They are quite happy staying as a singular atom because they've got that full outer shell of electrons and they are stable.
Got it.
Okay?
Your video's off and your video's on.
Okay, so linking to group 1 then. So group 1, lithium, sodium, potassium. Hopefully you've seen these demonstrated at school. They're quite unusual in that they're a soft metal. They're really quite reactive and they have a low density. Whereas when we talk about typical metals, when I think typical metals, I think of like door handles, chairs, chair legs, table legs, things like that, grates outside on the roads. They're not reactive, you know, they've not got a low density, they're quite strong metals. We also know that group 1 elements have 1 electron in their outside shell. Okay. So table 2 to show the electronic structure of a potassium atom. Okay. It tells us that we've got 19 electrons. Okay. So we've got 2 in the first shell, and the way that we write them, so we're going to follow this sort of pattern. The way that we write them is when we've got a full shell, we put a little comma to show that we are moving into the next shell. Okay, so 2 electrons, 8. So far we've got 10 into the next shell, 8, and then 1 in the outside shell, which makes sense because we've got 1 electron in that outside shell. Okay, why do group 1 elements have similar chemical properties? Okay, the way that something reacts is all to do with the number of electrons. Does it want to gain them, lose them? Okay, and so if it wants to gain or lose, it will be more reactive. Your group 0, because it's got a full shell, they don't want to lose or gain, they're quite happy on their own. So the reason that group 1 have similar chemical properties is because they've got the same number of electrons in their outer shell. The ones on the inside, they are not involved in the bonding, and therefore they don't contribute to it. So it's just those outer shell electrons. Okay, table 3 shows the observations made when lithium, potassium, and it's given us rubidium as well. Rubidium's not one that you've probably observed at school. You may have seen it on a video clip, but it's given us what happens. Okay, and then give 2 observations you can make when sodium reacts with water. So if you're a little bit unsure, look at what the other ones are doing. Okay, so lithium, there's bubbles slowly, floats, move slowly, and then as we've got down to potassium, it bubbles very quickly, melts into a ball, floats, moves very quickly, and we get a flame. Okay, so this one we're going somewhere in between. Okay, so we could say here, go somewhere in between, bubbles quickly. Yeah. Floats, moves very quickly, moves slowly. We'll go somewhere in between, moves quickly. So if you've seen these, they sort of phase move around on the surface of the water quite quickly, etc. Yeah, hopefully we've seen those. Okay, oops. Let's grab a quick drink. Crack on. Okay, so sticking with group 1 then. How does the reactivity of the elements change down the group? It's just worth 1 mark, so it increases. Yeah, that's all we would need there. Increases down the group. Give 2 ways in which the observations in table 3 shows the change in reactivity. So let's just pop back a slide. We've got things here, bubbles slowly, bubbles very quickly. Yeah, moves slowly, moves quickly. We've now got a flame involved when we look at potassium and explodes with rubidium. Okay, so we can see those differences. Even if we're unsure about what we've put as our sodium, look at what's there because that's the information that was provided, that's what's correct. Okay, so 2 ways in which it shows. So it bubbles more quickly. Oops. And we could say that lower down we get, how did it describe it? Get a flame. Potassium produces a flame. Okay, now if you'd related it to any of those, so it moves, it's moving more quickly, it's bubbling more quickly, either are fine. Okay, so which gas is produced when group 1 elements react with water? Okay, so they are producing hydrogen gas. That's why we get that little bit of a flame, because it produces hydrogen gas. As it's reacting, it's producing heat, and so that hydrogen actually ignites later on because the heat that it's producing causes the hydrogen to ignite, because hydrogen is a flammable gas. Okay, so the higher end of this type of question then is about explaining why the reactivity gets higher as we go down the group. Okay, so we've already kind of covered the first part of it because we've looked at the observations, looked at what happens. Okay, so talking about that it floats, melts, moves around, we do get a bit of a flame with potassium. Yeah, so just 2 of those. So floats, melts, moves around the water, fizzing. Fizzing is always a good one. Right, so let's talk about this one to explain why the reactivity changes as we go down. So if we think about lithium, we've got 2 shells of electrons and 1 in the outside shell. When we move down to potassium, I'm not going to draw all the electrons, but we're now, oops, lost my shell. We're now in that 3rd shell and that electron on the 1 electron in the outside shell. So remember when I said that reactivity is about, do they want to lose or gain electrons? Have they got a full outer shell? Do they need a full outer shell? Okay, so what group one want to do is they want to lose this outside electron. They want to get rid of it. Okay, so as we go down the group, okay, the outer electron is further from the nucleus. That's because the atoms get bigger, so we have more shells of electrons. Okay, so if you think we've got our positive nucleus here in the middle, and it's attracting those negative electrons, because we've got another shell of electrons, we're further away. So we've got a greater distance. So that means there's less attraction between the nucleus and the outer electron. I kind of think of it having two magnets. Hold them quite close together, you'd feel that pull. The further away you hold them, the less attraction there will be. So because that outer electron is further from the nucleus, there is less attraction, and so it's easier to lose that electron. Okay. To explain why the reactivity elements changes going down group one, it increases, they get more reactive. We know that if you've seen them or from that kind of table of information, they get more reactive down the group. Reactivity increases because the outer electron is further from the nucleus. There's less attraction between the electron and the nucleus, and therefore it's easier to lose. Okay, so group 7. So group 7 is the reverse. Group 7 decreases in reactivity down the group. Okay, so we'll just put a little reminder. We've got fluorine, chlorine, iodine. And what we can do here, so we've got a student mixes solutions of halogens, so our group 7, with a solution of their salts. Table 1 shows the students' observations, so they're writing down what they saw happen. Okay, so what we're looking at is what halogen we've got. So we've got chlorine, and then we've got 3 salts. Potassium with chlorine, so they're all with potassium, but we've got chlorine, bromine, and iodine. Okay, now what we're noticing is then when we've got chlorine, so when we have chlorine and we put it in with bromine, we get a colour change. Let's add that one in so we know what we're talking about. So when chlorine goes in with bromine, we get a colour change. When chlorine goes in with iodine, we get a colour change. Okay. So what you can deduce from this is the reactivity increases, reactivity decreases down the group, or you can say that it gets less from chlorine to iodine. Doesn't matter how you word it. And the reason that we know this, these are displacement reactions. We get that colour change because that chlorine has displaced bromine. So bromine ends up on its own, and we see this colour change. So using an example, put in an example. So chlorine has 2 reactions, or chlorine displaces bromine and iodine. It doesn't matter how you've worded it. So what we're noticing is that the ones that are higher up are having displacement reactions, whereas the ones at the bottom do not react. Okay. It's explaining that reactivity. And then the last one on here, whoops. Sorry, this is the one I wanted. So group 0, not much happens with group 0, full outer shell, therefore they're not reactive. They do have uses. So we have helium, which is used in sort of balloons and in weather balloons. We've got neon that goes into lights, argon that produces the atmosphere. We could put it into like light bulbs so that it doesn't get too hot and the doesn't react with the oxygen, explode or anything like that. So going back to the fact that they've got a full outer shell of electrons, they don't want to gain or lose any, they don't want to do any bonding, they're quite stable on their own. So they exist just as single atoms, monatomic, just on their own because they've got a full outer shell and they are stable. So 2 marks explain why group 0 elements are monatomic. So we need something along the lines of that they have a full outer shell. It's fine to say that they have 8 electrons in their outside shell. Yeah, they've got a full outer shell. They do not need to gain or lose electrons. Okay. Right, last bit then. So this is for separate sciences only, because we're looking at transition metals. More than welcome to leave if you don't need separate science. If you want to stay and listen to the questions and look at how to answer those questions, more than beneficial, more than welcome to. Okay, so transition elements, metals, sorry, are that midsection. So that's a section that Mendeleev didn't have. And so it's about comparing them to group 1 because they are, group 1 are soft, reactive, we were talking about earlier, whereas these are more called typical metals. And so a great example is like copper. So it's much more solid, they're much stronger, yeah, they're more dense, they're not as reactive, etc. Okay. So these are quite straightforward. It's usually a comparison. Compare transition metals to group 1. Okay, so 2 statements. Which 2 statements, sorry, are properties of most transition metals? Okay, so remember, think it's usually about that comparison to group 1. So tick 2 boxes. So soft, no, they're the group 1. Group 1 are soft, they're more dense, okay? They form colourless compounds. They form ions with different charges, have high melting points and low densities. Let's rule out that density. We know that's group 1 because they float on the water. So they must have a low density, okay? Now colourless. Okay, put that in because they form coloured compounds, they don't form colourless. So that's just a little play on the word to make you think about that. So they do form ions with different charges because they've got a different number of electrons in their outside shell. Group 1 have got 1 electron in their outside shell, so they will always become +1 ions because they can lose that electron. Whereas because these have got lots of different electrons, they might lose 1 electron and become +1, they might lose 2 and become +2, etc. And they have high melting points because in comparison to the group 1, we said that they're much stronger, they're much sturdier. These are your typical metals, door handles, grates on the road, etc. Yeah, so they've got high melting points. When we put them into water, they wouldn't melt like group 1 do. Okay, It gives you an example now that iron is a transition metal and sodium is a group 1. 2 differences between the properties of iron and sodium. Okay, so there's lots that could be said here. So I'm going to flick up the mark scheme because there's lots of things. So we've talked about that our transition metals have a higher melting point, higher boiling point, they're denser, they're harder. You kind of said these in what's called the converse. So if you just said that sodium has a lower melting point, boiling point, it's less dense, it's not as hard, that is acceptable too. Iron is stronger, less reactive. It has ions with different charges, form coloured compounds. If you know that iron is magnetic, yeah, and group 1 is magnetic. So there's lots that could be said there. All you need to have done is to state 2 of those. So again, it's about that comparison, knowing that group 1 are reactive, they're soft, they've got low density. Transition metals, kind of the opposite. They've got high density, they're much harder, they're not as reactive. So this one gives you again a name of a typical transition metal. Put a tick next to the 4 properties that you would expect. So if you think in transition, if you know their properties, what are you expecting from them? Okay. Forms coloured compounds, has a high melting point, is strong. Yeah, so they're the most obvious ones. And just knowing that metals in general conduct heat. Cobalt is mixed with other transition metals to make alloys. So we alloy things to change their properties, alter their properties, etc. These alloys are used to make cutting tools, which remain sharp at very high temperatures. They can cut through other metals. Suggest 2 properties of transition metals that make them suitable for cutting tools. Okay, so let's have a look. Sorry, we'll lose this ticks, but it's fine. So I'll see if I can make that a touch bigger for you. So again, any 2 of these, if we want them to be useful as cutting tools, well, it's told us here that they remain sharp at high temperatures because we don't want them to melt and change shape because you could lose that sharpness. So we can have high melting point or withstand the high temperatures. We want them strong and tough. We don't want them brittle. So brittle means that they will break quite easily. We don't want them brittle. They're hard. Yeah, we don't want them to change shape. They need to stay as they are. And they're not very reactive. Because if they were reactive, as they were whizzing around and generating that heat, they could react. Okay. Right, guys, whistle stop tour of module 1. Thank you very much for joining this evening. I have now got another session. So if there are any questions, please feel free to email me them over and I will answer them at another point. Okay, guys, thank you very much.